Hello everyone and welcome to another video. In this one we will be starting exactly where we left last time, and I think we can improve our list data structure or our list macros a little bit, right? So the first clear improvement is to prevent these kind of situations where we need to type def a specific type into a word so we can use the declare macro. And one way to prevent this is to define a type and a type name. So now we need to provide two parameters to our macro, and we can simply replace all of this code by, actually we need to replace I can remove all of this, because since now we specify exactly the type name of the list, we should, instead of using this predefined type, we should actually just use something like type name and then concatenate it to the type or something like that, right? Actually concatenate it with node, right? So we should concatenate it with node, and since we are no longer using this type def trick, we can move this here down, and we can say type def that, right? We can say type def that, and here I don't know if I want to have an underscore here or not. I probably, I don't know, I'm not going to add any underscore, I guess. Yeah, I'm just going to leave it like this. And here I'm going to need to do something like struct and then this type, so I can refer to the same type, but since this type def is not does not come before the struct declaration, I need to include this keyword in here, right? So now I can do a similar thing for this case, right? So I can do type def, and I'm no longer going to use any of this, and here I'm just going to use type name. So we are just going to define a struct with the same type name that we pass to the macro, and in this case here we can simply use this type, right? So we can simply use that type, and now this is much shorter. We can simply move all of these slashes forward, right? Something like that. I don't know why this slash is so outside of place, but let's keep going. Something like that, right? Something like that. And I can tab it like so. Alright, just to be a little bit more readable, right? And easy to understand what's going on. Alright, so this code no longer compiles because it is complaining. Oh, it is complaining obviously about t data, because now we need to use the type here, right? So we need to define data with the specified type. Alright, so now we should in theory be able to do something like this: sharp pointer and sister something like list sister or something like that, and here we can do floats, and we can do list float. Alright, so list of floats. And just to be completely correct, I think it is a good approach to wrap this type around, right? Just wrap that type around so we can have maybe, I don't know, maybe we can pass type off in here or something like that, right? So that's more user friendly, right? So what is this complaining about? It is complaining expected an identifier, because we actually are not allowed to do that. So yeah, alright, so we can only do this. Alright, so now we have changed the list declare macro to specify the type and the type name, and I think we can test it by just modifying this. Alright, and we can compile and run our code. I'm going to use the same command we used last time, but with wall, werror, and pedantic, so we can be sure we are not doing anything weird, right? Alright, so this complains about a lot of stuff but I have no idea what it is complaining about. I think I'm using the same development kit. Oh, I'm using the wrong development kit. Alright. I get it. So this uses version 12.2, so this is not the C23 version or C2X version, right? So that's why it is complaining about implicit declarations of type off and all of that, because I'm using the Relief development kit, and I have another development kit with the correct GCC version. So let me change to that one. Alright, so now I have the correct development kit, right? I have the one who has the most recent version of GCC, so that's all good. And now I can actually compile it. Let me re-add the wall, werror, and pedantic, right? And alright, so now this is complaining about other stuff. So struct list footnote from incompatible pointer type. Alright, so this is basically, so I think that to have this working, I need to actually do type def struct I don't know, let me say that underscore s, since this is not going to be used anywhere, right? Since this is not going to be used anywhere, this is internal to the macro. I can say something like that. So let me just test my theory with this and check if this is the actual problem. Right, so I can change that. I can change that, and I can change that. Let me check if this, okay, so this is complaining because I see a semicolon here, and this still complains about something. Expected an identifier, so because I have this in the wrong order, so this should be like this. Actually, I am confusing stuff. This should be like that, right? So this should be like this, and this should actually be correct. Let me test it. All right, so this is now working. So we actually need this type def here, and I want to make it as internal, so as hard for the IntelliSense and all of the autocomplete features from editors to pick it up. So I think I'm going to just put an underscore here, right? So I'm going to put an underscore here to denote that this is internal to the application. Then I'm not going to add anything after this, right? So because these prefixes can sometimes be picked up by syntax and grammatical stuff, and actually be parsed as types, and I don't want that. And now I can simply do this, so we are just redefining the struct this as the type. We define the struct, then we can do this, and then we can do this. So this should still work, right? So we can test that. This does in fact still work, right? So let me just reorder that, right? Just reorder that. Alright, so this now list declare macro is going to generate me an internal type, right, that is only going to be used internally for these macros, right? So the user should not be aware of it. And it's going to also generate me a node struct and a list struct, right? Exactly. All right, so I think this is more or less the behavior I want, I think. Well, I think I can even do slightly better because, well, because this type name, well, just for OCD purposes, right? Just for OCD purposes, I'm going to do that, right? Put an underscore there, and I'm just going to use that as the actual type name, right, of the node. All right. Since I only have one internal type, I can just prefix it and suffix it with underscores and use that as the node. All right. So another thing I would like to do is to compact this stuff. So some of you may have realized that we can extract this code right here from here into a different right, yeah, we can extract this code outside of this if else statement, right? So we can simply do that. And in here we can also assert, by the way, we can also assert that list begin is null, right? Because if the end of the list is null, then the beginning of the list must also be null, right? Must also be null. So we have that stuff there, and we no longer need this, right? So we can delete it, and now our code is a little bit more compact, right? It's a little bit more compact. What else can we do? Right, this for each, I think it's more or less working properly, and I think that's pretty much it. So these were the improvements I wanted to make to our list macros, right, at least for now. Alright, so I think this is a more clean approach to the code we created in the last video. Another thing we can do is, instead of saying list for each, we can just say list for, and yeah, so the name is more compact and it resembles more the for keyword in C, right? And actually I think that's everything, to be honest. Alright, so now we can start thinking about allocators, right? And there is a specific allocator I would like to implement. It is called linear allocator, right? A linear allocator. Let's search it in Wikipedia. Also known as an arena allocator or region-based memory, whatever. It has many names. So this is a region-based memory management. It also known as zone, arena, area, or memory context. It is a linear allocator since each region has a single pointer, right? It bumps the pointer upwards, and we can have multiple regions inside of it, right? And a very simple approach to this would be to have a linked list. That's exactly what we are going to do. And each node in the linked list is a region of the arena, right? And then if we want to allocate stuff we can simply traverse the linked list and see if one of those specific regions has enough memory for our allocated for the amount of byte we want to allocate, and if that's not the case, we can always append a new node into our arena, right? Alright, so that's basically what we are going to implement in C for our program. So I think we can start. Alright, so I think that the first thing we can do is to create a struct that holds our region. So we can say something like typedef struct region. Alright, and a region is going to contain a few things. The first one is the capacity itself, and I think I'm going to store it in size t, capacity, and the other thing is the current length or size. I don't know if I want to call it length or I want to call it size or count. Let's call it length. Why not, right? And now we want to store the data, and that's a catch already, right? And that's something we need to consider. So we could store the data as an array of char, right? So 8-bit values, right? 1 byte. But that would basically prevent us, or it would create scenarios where the memory is not aligned, right? And we would basically return to the user pieces of memory that are not word aligned. And I want to return word aligned allocations, right? So one way to do that is to create instead of storing our data as chars, we can store our data as uint pointer t, and this basically this type in C basically will always have the size of the word that the program will always have the size of a word of the machine the program is currently running on, right? So in a 64-bit machine, this is going to be 64-bit. In a 32-bit machine, it's going to be 32-bit, and so on and so forth. It probably also supports more exotic sizes, I guess, right? And it is also part of the C standard, right? So I think it is in standard def, right? Standard definition, right? All right, so now we probably want to create a function that given let me say, I don't know what I want to call it. Maybe I want to call it new region, something like that. I don't know if I like this name. I probably want to say something like region or region underscore new. I don't know what to call my things. Yeah, let's call it just new region for now, right? And this is going to return me a pointer to region, and it's going to receive capacity. And we must take note that this capacity and this length are actually words, not bytes, right? They are actually words, not bytes. So here, this is going to be an array of words, right? So we need to keep that into account. So we can say, so new region, and now I need to create a region with this amount of capacity, right? So for this allocator, so we are going to build a faster allocator using a slower one, and our slow allocator, right, in air quotes, is going to be malloc, the same one we're using here, right? So we are going to allocate our regions with malloc, and then we are going to use the new and improved allocator in the rest of our program, okay? I could use the virtual alloc and mmap, so from Windows and Unix systems, but I think I'm just going to use for now the standard libc malloc function, right? Okay, so now we can simply say this is our result. And another thing is that I don't know if I want to zero initialize all of my allocations. Maybe I want, maybe I don't want it. Maybe the initialization is going to be the responsibility of the user, and maybe that's the best approach because it's probably faster, since most allocations are not going to need to be zero initialized, right? So for now, I'm just actually going to use malloc, but in the future, if I need to zero initialize data, I can use calloc here and then memset in other places, right? That's not too hard to do. So I can do malloc, and I need a size in here. And this size is the amount of bytes, right? But we need to take into account that this capacity is in words. So to convert words into bytes, we can simply say that our size is going to be the capacity times the size of a single word, right? A single word. So this is going to be the thing we want to create, and this is going to be the size, right? And now we can assert that the result is not null, so we can simply say that. We can assert that the result is not null, and we can initialize the rest of the data. Actually, I made a mistake because here I can actually call it, let me, capacity in bytes. So this is capacity in bytes, but I also need to allocate the size for the struct itself. So I need to allocate the size of the region itself, the struct, and the data, right? The data that this struct is going to hold. And this is a feature from C11, if I'm not mistaken. So arrays without right, so basically pointers at the end of structs, they will hold any extra bytes you allocated, right? So this is going to automatically contain capacity bytes in here, right? And this is going to represent this, right? So this is contiguous memory. All right, so now I can actually initialize stuff. So I can say result capacity is going to be equal to capacity. Result length is going to be equal to 0 for now. And the data is already initialized as I have explained, since this is contiguous memory and this is supported by C11. I believe that's the actual version of C that started to support this feature. Alright, and now I can simply return the result. Okay, so now we have our region, and we need to create the list, but that's the most interesting stuff, right? Because the region is actually going to contain a link, so I can say something like that, right? And I need to modify this a little bit, because the region actually needs to contain a pointer to the next region, right? Since this is going to be a linked list, it is the same approach we followed here, right? So the node contains a link to the next node and the data itself. The only difference is that this linked list node contains more fields than the data itself, right? All right, so now we can actually create a type def struct arena, right? and we can create our struct that is going to contain the fields for the arena. And I think that we are only going to need the first region, if I'm not mistaken. So we can simply say begin for now, right? We can simply say begin for now. And the only function we need for the arena is going to be void pointer arena hour. And this is going to receive an arena and the amount of bytes, right? So basically this function is going to allocate this amount of bytes in using this specified arena, okay? And now we come to the same problem we had here, right? So we have this amount of bytes, but we need to convert them into a capacity, right? Because our new region function accepts a capacity in words and not bytes. So this is where the trick comes, because since we are converting our bytes into words, our region capacity is always going to be word aligned, because to convert our bytes into words, we can simply say, let me think if I don't, let's actually call it here capacity, or actually size in bytes, and this is going to be simply size, and size is going to be, so in a perfect world we would be able to do something like this, but this would be incorrect, right? So this would be incorrect because we could actually return a capacity lower than the equivalent amount of bytes, because this could truncate it, right? So to have actually a correct and word aligned size, we need to here we need to add size of uint pointer, if I'm not mistaken, right? So we add a word into our bytes, so a word size into our size bytes, and then we can divide it by the amount of the size of a single word, right? And this is going to give us the correct and word aligned amount of words that we want to allocate. All right, so now we basically need to traverse all of our arena while we don't have a region with enough capacity for our allocation. So we can say something like for region, let's say region is equal to arena begin, and while the region length plus the size is greater or equal than the region capacity, right? So if the current allocated space of this region plus the size we want to allocate is greater than the capacity, then we need to keep searching for a free region. And I also want to add to this condition the thing like this, because we only want to check this if the region is actually it does actually exist, because here I forgot to initialize it. Good thing I remembered, because here the link is going to be null, right? Here the link is going to be null. We can do that, and I can simply say region is equal to region dot link, right? Okay, so now that we have all of this stuff in here, we should be able to do nothing. So yeah, that is very interesting. So I probably don't actually want this to be a for loop. This is probably better off being a while loop. So I can say something like this. I can move this into the while, and I can move this to the inside of the while loop. Right? I can say something like this, and this is probably a lot cleaner. And yeah, so we keep traversing the arena while we don't, either while we have regions or the we haven't found a region with enough capacity. All right, so here we have an option, right? If and this is actually while region dot link exists, right? So we want to traverse our arena while there is a next region, and the current region does not have enough capacity for the allocation we want to do, right? Okay. So here we can check if this, so if the current region does not have enough capacity, then we know for sure that there is no other region inside the arena that could hold our allocation, right? So to handle that, we can simply say region.link is equal to new region, and we can say size, right? We can simply allocate this amount of bytes, this amount of words, and we can assign the current region to be equal to the next region, right? So that's the stuff. And finally, at the bottom, we know for sure that this region, right? This region can allocate this amount of bytes, right? So we can simply say that the result we are going to return to our user is going to be region.data region.length, and this is going to be a pointer, and then we need to increment the allocated length, so we can say length plus equals size, and we can simply return result, right? We can simply return the result. And there is one thing that I forgot, right? I didn't really forgot, I just didn't want to cut my reasoning. So I can simply say if arena dot begin, so if this is not allocated, so basically we need to also handle the initialization of the arena. So if the arena begin does not exist, then we need to for sure allocate a new region. So we can simply say that, right? We can simply say that, and we can say that arena begin is equal to new region. And I think that's everything. Oh, yeah, I think that's everything. So I can actually inline this. And the last thing I would like my allocator to have is a default capacity. And for now, my default capacity is going to be 4 kilobytes divided by whatever size of word it is. So I'm always going to allocate 4 kilobytes. I think that's a good stuff in there, right? So I'm always going to allocate 4 kilobytes. All right. And finally, I can add this new variable, say capacity. And I can say that the capacity is equal to the default capacity, and then I can say if the size we want to allocate is greater than the capacity, then capacity is equal to this size we want to allocate, right? So whenever we call new region, we can actually pass the capacity, right? So anytime we allocate a new region, we are always going to allocate it with either the minimum capacity or the size the user provided, if it is greater than the default capacity. This is actually not really the default capacity, this is the minimum capacity, right? Because this is minimum capacity, because this is always going to be used if size is less than this, right? Alright, so I think that's pretty much it. This is the entire implementation for the Arena alloc. Alright, and I think I'm going to just test this code for now, and I can leave any other feature for a future video tomorrow or something like that. So let me just add a new line here, and I can say something like arena. This is going to be our arena. We can zero initialize it, and let me say I want to allocate I don't know, 3 integers, so I can say arena alloc, we pass the arena, and I can say size of int times 3, right? So we allocated 3 integers. Yeah, and let me say see if this actually works. So I can say something like this. Oh, this is complaining because it is unused. Well, let me just print the pointer to this variable, right? So, oh, this is not what I want, this is what I want. Void star, so I can say void star. Alright, so we basically allocated this this pointer and gave it to our user. So another thing I want to use or to print, it is probably the length of the arena.begin.length, and since I'm at it, I can also print the capacity, right? Alright, so we basically in this test basically defined a 0 initialized arena, and then we call arena alloc, and we try to allocate enough size for 3 integers, and here we print the pointer that arena alloc returned. We print the current allocated length in the first region of the arena and the capacity of that region, right? So let's try to run it, and as you can see, we basically allocated we returned this memory pointer. We are using 2 words. Oh, that makes sense, right? That makes actually a lot of sense. I'm going to explain why. So we are just using 2 words, and we have enough capacity for 512 words. So why are we using 3 words? Well, because an integer in C only uses 4 bytes, right? And I am inside a 64-bit machine, so this is the word, right? And this is the int. So a int has 4 bytes and a word has 8 bytes because I'm in a 64-bit machine. So I'm asking the arena to give me enough space for 3 times 4, right? And that's 12, right? So I need 12 bytes. And basically I'm basically allocating, or I'm reserving in this enough words that can safely fit 12 bytes, and that's basically 16 or 8 times 2, right? And this is 4 times 3, right? So I need exactly 2 words to fit 3 integers in C, right? Because 16 bytes can fit 12 bytes, right? So that is exactly why the first region in our arena, it's reserving 2 bytes, right? There is a little bit of waste, but I think it's a lot better to have memory aligned allocations than not have them like that, right? And we can always modify this if it's necessary. We can have specific allocators for non-memory aligned things and so on and so forth. So let me say I want to allocate now another thing. Let's say I want to allocate something else. Right, so this is going to be not a new variable. And now let's say I want to allocate, I don't know, 5,000 integers, right? 5,000 integers. So I'm assuming that after the second allocation, the first region is going to be completely filled. Actually, no. The first region is going to be, is going to remain the same. So the first region is still going to only have 2 bytes consumed. Is going to have the same capacity, and we are going to allocate a second region, right, with enough capacity to fill this entire location, right? So if I add another stuff here to my print function, and I say, so this is the first region, and I assume, or I hope my second region, so it's here going to be here, has enough capacity, like so. So I hope that this second region is going to be completely filled, right? It's going to have the length completely filled, and the capacity is going to be larger than the minimum capacity, right? Because we are asking our allocator to give me more bytes than the minimum capacity for each region, right? And since this amount of bytes cannot fit inside a single region, the first region that we use here is not going to be used, and we need to allocate a new one, right? So if I do this, I am expecting exactly, right? So as I hoped, in the first allocation, we created a single region. We consumed 2 words from that region out of 512 possible words. In the second allocation, since the second allocation is trying to allocate a number of bytes much larger than the region we currently have as available, we create a new region, right? We create a new region with that exact amount of bytes, and we completely use it, right? So we completely use it to the very brim, right? So I think this is the correct behavior, right? Or at least is the behavior I want right now. And I'm particularly happy with the implementation. I can change it in the future, but I'm more or less happy with it. And I think it's, yeah, I think that's everything for today. I may change the minimum capacity in the future, but besides that, I actually enjoy this quite a lot, right? So I don't think I have any complaints about this specific thing, right? All right. So in the next video, I would like to now change the list, the generic list macros to support, right? To support specific allocators. So I want my data structures, or my generic data structures, to have 2 implementations, or have to have 2 possibilities. One, to use the default allocator, and I'm still and I'm still thinking about what is going to be the default allocator. I'm still not sure to what I want. And another one, to specify a specific allocator. So I want to say, well, this append is going to use this very specific allocator, right? That's what I intend to use, right? But that's just going to be the next video or so. So I think that's everything for today, and see you in the next one.